Hello friends, this is Priyanka. Today we are going to solve a problem on torque voltage analogy. In this video, I will give you some important tips regarding how to apply torque voltage analogy and how to draw analogous electric circuit with the help of differential equations. Let us first understand what is the given mechanical system. Now if we observe this system, here the applied torque is T, which is input to the system. And what is the output? So output is given in terms of angular velocity omega 1 for mass moment of inertia Z1, omega 2 for the mass moment of inertia Z2 and omega 3 for the mass moment of inertia Z3. Now in between Z1 and Z2 there is spring with stiffness K1 is there, and in between Z2 and Z3 there is spring with stiffness K2 is there. Now for this mass, that is with moment of inertia Z1, there is the damper with viscous friction coefficient V1 is attached. Then in the same way for the second mass there is damper with B2 is attached, and for this third mass there is damper with B3 is attached. So this is the given mechanical system. Now in this system we can say that torque T is the input and output is in terms of omega, that is the angular velocity. Now both these terms, that is the torque and this omega, are variables with respect to time t. So while we are going to write the differential equation, we have to write the equation in terms of t and omega. So this is very important thing. Suppose here theta is there, that is the angular displacement is there, then we have to write the differential equation in terms of torque and angular displacement theta. Now we will first draw the free body diagram. So while drawing the free body diagram, we have to take these three masses with Z1, Z2 and Z3. Now if we observe this Z1, then here the applied torque T is related to Z1, then omega 1 is in the same direction of the applied torque T. So we have to show that. Then which elements are responsible for the reaction torque? So for the reaction torque, it is inertia for this Z1, then reaction for torque due to this spring stiffness K1 and the reaction torque due to this damper B1. So we can say that TJ1, TB1, TK1. Now we know that what is the equation. So equation in terms of theta we will first write and we will then convert into omega, so that you can clearly understand how to write the equation in terms of omega. So how we can write the equation that is for the applied torque T. So I will write here T is equal to J d square theta by dt square plus B d theta by dt plus K into theta. Now this J, B and K, these terms are here. Now we have to write this equation in terms of omega, because omega is output, that is given. So theta is nothing but, so we know that d theta by dt is nothing but omega, that is the, I will write d theta by dt is equal to omega. So how I can take this theta? So suppose I take both side integration, then I will get theta is equal to integration of omega dt, and d square by d theta, d square theta by dt square is nothing but d omega by dt. So these are the replacement that we have to take here. So how I can write this equation? T is equal to J d omega by dt plus B into omega plus K into integration of omega dt. So this is the equation, so I will underline. So this is the form of equation that we have to take. Now if we observe the free body diagram for this J1, then we have to define all these torques in terms of omega. So how we can write the differential equation? According to Newton's second law of motion, we can say that input is equal to sum of all reaction torques. So input equal to Tj1 plus Tb1 plus Tk1. Now we will write the equation. So for this Tj1, J1 is having angular velocity omega 1. So how we can write here? This is, instead of J, I will write J1 d omega 1 by dt. So I will write here J1 into d omega 1 by dt plus. Now for this Tb1, so B1 is attached to only J1, which is having angular velocity omega 1. So how I can write here? B1 into omega 1. So instead of B, I have to take B1 here. B1 into omega 1 plus torque related to this K1, that is the reaction torque due to this K1. Now this spring is in between J1 and J2. So I have to take the difference for this omega 1 and omega 2. But this is the free body diagram of J1. So I will, while taking difference, I will take omega 1 first. So I will take here K1 integration of omega 1 minus omega 2. Bracket complete dt. And on the left hand side we have to write torque T, and it is the variable with T. So this is the equation, or we can say this is the differential equation, and I will give here the equation number 1. Now we will move for the second free body diagram. So for this Z2, which terms are related or which elements are related? Now if we observe, here is K1, then K2, then B2, and inertia torque due to Z2. So we have to write all these, and omega 2 is related to this Z2. So I will write here omega 2, then reaction torque we have to show in the opposite direction. So here torque due to Z2, torque due to B2, torque due to K1, and torque due to K2. So according to Newton's second law of motion, we can say that the summation of all the reaction forces is equal to 0. So how I can write this? That is Tj2 plus Tb2 plus Tk1 plus Tk2 is equal to 0. Now I have to define all these torques in terms of omega. So how we can define here? So I will write here. Now for this Z2, I will take Z2 d omega 2 by dt plus. Now for this B2, I will take here B is connected to Z2, which is having angular velocity omega 2. So I will take B2 omega 2. Then for this K1, so for this K1 we have to take the difference in between these angular velocities. But this is the free body diagram of Z2. So I will write here omega 2 minus omega 1. So how I can write here for this K2, that is for this K1. So first I will take K1. So K1 integration of omega 2 minus omega 1. Bracket complete dt. Plus, now for K2. So again K2 is in between omega 2 and omega 3. So I have to take the difference, and we have to take omega 2 first. That is for K2 in the integration of omega 2 minus omega 3 bracket complete dt is equal to 0. So this is the second differential equation. Now we will move for the third. So for this third Z3, element K2 and B3 and inertia torque due to Z3, these three elements are responsible for the reaction force, where omega 3 is nothing but the angular velocity, and we have to show the opposite direction, that is the reaction torques in the opposite directions. So I will take here summation of all reaction torques is equal to 0, that is Tj3 plus Tb3 plus Tk2 is equal to 0. So how we can write here? That is J3 is having angular velocity omega 3, that is J3 d omega 3 by dt plus B3. So B3 omega 3 plus K2. Now K2 is in between J3 and Z2. So I have to take the difference, but this is the free body diagram of J3. So while taking difference, I have to take omega 3 first. That is K2 in the integration of in the bracket omega 3 minus omega 2 bracket complete dt is equal to 0. So this is the third differential equation. Let us first understand how to apply torque voltage analogy. For that we will consider one electrical network where voltage is input. So in this network, resistor, inductor, capacitor are connected in series, and output is in terms of current I, and current flowing through all these elements, that is R, L, C, is same because these are connected in series. Now how we can define this current I? So current I is nothing but rate of change of charge Q. So I is equal to dQ by dt. Now how we can write the equation for this electrical network? So V of t is equal to L d square Q by dt square plus R dQ by dt plus 1 by C into Q. But we have to define all these elements, that is resistor, inductor, capacitor, in terms of current I. And current I is nothing but dQ by dt. So instead of dQ by dt we can put here I. And what about Q? So if I take both side integration, then integration of I dt is equal to Q. And d square Q by dt square is nothing but di by dt. So how we can write this new equation in terms of current I, that is V of t is equal to L di by dt plus Ri plus 1 by C integration of I dt. Now if we observe for the given mechanical system, what is the equation in terms of torque and angular velocity omega, that is T is equal to J d omega by dt plus B omega plus K integration of omega dt. Now I will give here this equation number 1 and for this equation number 2. Now we will compare the elements. Now torque is input, voltage is input. So torque is analogous with voltage. Then for this B omega, and here is R and I. So I will say that B is analogous with R. Then K is analogous with 1 by C. Now integration of omega dt is analogous with integration of I dt. Then I, that is I and omega, these are the coefficients. So we can say that omega is analogous with I, and for d omega by dt we can take here as a di by dt. So these are the elements. Now we will apply the analogy to this mechanical differential equations. So this is the first differential equation. So for this torque I will write here V, that is V of t is equal to, for this J1 I have to consider here, for this J, I have to write here as a J is analogous with L. Now for this J1, that is we have to consider the suffix 1 and 2. So for this J1 I will write L1. So I will write L1. Now d omega 1 by dt, that means I will write di 1 by dt plus B1. So B1 is nothing but R1 and omega 1 is nothing but I1 plus K1. So K1 is nothing but 1 by C1 integration of omega 1 minus omega 2, that is I1 minus I2 dt. So this is the equation. Then we will move for the next differential equation, that is J2 d omega 2 by dt. So J2 is nothing but L2 d omega 2. So what is d omega 2 by dt? That is di2 by dt. di2 by dt plus B2 omega 2. So for this B2 I will take R2 I2 plus K1. So for this K1 I will take 1 by C1 integration of omega 2 minus omega 1, that is I2 minus I1. I2 minus I1 dt plus K2 omega 2 minus omega 3, that is I2 minus I3 dt is equal to 0. Now we will move for the third differential equation. So here Z3 d omega 3 by dt, that is L3, and d omega 3, that is di3 by dt plus B3, that is R3 I3 plus K2. So instead of K2 I will take 1 by C2 omega 3 minus omega 2, that is integration of I3 minus I2 dt is equal to 0. So these are the three differential equations, and from these three differential equations we have to draw analogous electric circuit. Now we will observe these three differential equations and we will make here some data regarding coefficients of resistor, inductor and capacitor. So we will move for the first differential equation. So for this first differential equation, voltage is the input. Now for this inductor L1 is a long current I1, because coefficient is in the form of di1 by dt. So I will write here L1 is a long current I1. Then R1 is also a long current I1. Then C1, 1 by C1, that is capacitor C1 is in between I1 and I2. So for this C1 I will write here it is in between I1 and I2. Now we will move for the next differential equation. So for this L2 it is along the current I2. Then R2 is along current I2 and C1 is in between I1 and I2. And C2 is in between I2 and I3. Now we will move for the third differential equation. L3 is along current I3, R3 is along current I3 and C2 is in between I2 and I3. Now this is the rough data and it will help us to draw the analogous electric circuit. Now we know that when the elements are connected in series, then the current flowing through those elements is same, and when they are in parallel, then the current flowing through them is different. Now if we observe, there are total three currents, that is I1, I2 and I3. So for that I will draw here three loops parallel to each other. So this is the first loop, second loop and third loop. Now in these three loops, three different currents are flowing because these are parallel to each other. So for this first loop current I1 is flowing, for this second loop current I2 is flowing, and for this third loop current I3 is flowing. Now if we observe the first differential equation, V of t is the input. So and it is applied with this current I1 which is having inductor L1 and resistor R1. So this is the first loop which is having current I1. So I have to show here this V of t, that is the input voltage V of t. Now for this first loop, if we observe L1 and R1, both are having same current I1, and for this capacitor C1 is in between I1 and I2. So I have to draw this circuit. I will show here inductor L1 having current I1, then resistor R1 is also having current I1. Now what about capacitor C1? So it is having both the current I1 and I2. So these two are parallel loop and we have to show here the capacitor C1. So I will show here C1. Now we will move for the next differential equation. So L2 is having current I2, R2 is also having current I2. So this is the second loop which is having current I2. So I have to show here inductor L2 and resistor R2. Now if we observe, this C1 is having I1 and I2, so we have already shown. And what about C2? It is having I2 and I3. So in between this I2 and I3, I have to show here as a C2, that is capacitor C2. Now next is inductor L3. So L3 is having current I3, R3 is also having current I3. So we have to show for this third loop, I will show inductor L3 and resistor R3. And this capacitor C2 is in between I2 and I3 is already shown. So this is the analogous electric circuit for the given mechanical system.